Scattering from a dielectric slab. Let's look at the general case where we have some slab of dielectric in the middle here. We're calling this medium 2. To the left is a semi-infinite medium 1. Semi-infinite meaning it ends here, but it continues to infinity to the left, and of course also up and down. And then on the right, medium 3 is another semi-infinite medium, meaning while it ends here at its left side, or the right side of medium 2, it continues to the right off to infinity and also up and down. And so this is the dielectric slab we're talking about, medium 2, and it has a thickness D. On the first interface, going from medium 1 into medium 2, it has a reflection coefficient R12. Now, a wave going the other way would have a reflection coefficient R21. They differ because the wave's going different ways, and you'll notice they differ in the order of the terms in the numerator, which really means they just differ in sign. So in fact, R21 will be the negative of R12. Likewise, we could talk about a wave transmitting through that interface. We have a T12, and that's related to R12 through 1 minus R12. And then a wave going backwards, we have a T21, which is related to R12 as a 1 plus R12. And I won't go through it, but on the other side, we have another reflection coefficient R23 and a transmission coefficient T23. We don't have to worry about R32 or T32 because we do not have any waves incident from the right. We do have a wave incident from the left, and it will reflect, and then it will also transmit. Now, a phase or a wave will accumulate phase as it propagates through this material, and so that phase psi is K naught times the refractive index times the length of this slab. Okay, so let's start with this analysis. We have an incident wave, and it'll have an amplitude E naught. What happens at that interface? Well, one of two things. Some of that can reflect, and some of it can transmit. So how much would reflect? Well, we take the amplitude E naught, and we multiply by this reflection coefficient R12. So remember, this R12 E naught is really the amplitude of the field immediately at this interface. And even though I'm showing it a little bit of distance away, it's immediately against the interface, but in medium 1. Likewise, this term T12 E naught is immediately at the interface, but on the medium 2 side. And so it has a starting amplitude of E naught, but we multiply that by a T12, the transmission coefficient. From there, we have this transmitted wave, and it progresses through the entire slab, so it accumulates phase. How much phase does it accumulate? Well, it's e to the minus j psi, where this psi is the K naught N2 times d, the amount of phase the wave would accumulate. Well, we have a wave now incident on this second interface. So one of two things can happen. Some of it can transmit, and some of it can reflect. So how much transmits? Well, the incident wave here is T12 E naught e to the minus j psi. And so that's this part of the expression on the right, the T12 E naught e to the minus j psi. So these three terms here are the incident wave. And so we tacked on a T23 to give us the wave that transmits through the interface. And this expression is valid for a wave immediately at the interface, but in medium 3. Now we can also reflect. So we can take this expression, which we see down here below, and tack on an R23 to quantify how much reflected. From this point, we have the reflected wave that will traverse backwards and accumulate another e to the minus j psi of phase. So the field on the left is the same expression as the field on the right. However, since it accumulated another e to the minus j psi of phase, we now have the phase as e to the minus j 2 psi. Now we have a wave incident right to left at the first interface again. One of two things can happen. It can transmit and it can reflect. Well, how much transmits? We'll take this expression as the incident wave, and that's what I'm circling over here on the left, and we tack on a T21, meaning transmission from medium 2 into medium 1. And some of this can reflect. So we take this expression for the incident wave, that's down here that I'm circling, and we tack on an R21 for how much has reflected. At this point, this reflected wave, which is now reflected twice already, transmits through this second medium, and it accumulates another psi of phase. Otherwise, the expression's unchanged. But now we have an e to the minus j 3 psi. Well, some of that can transmit, and some of that can reflect. The amount that transmits, well, we tack on another T23. Otherwise, this is the expression of the incident wave. We can also take the expression for the incident wave, and we tack on another R23. So I'm writing this now as an R23 squared, and it's squared because there's a second one there. Maybe it would have been a little bit simpler if I didn't square it and then wrote a second R23 out here, but I chose to combine them. This wave now travels backwards through the layer, accumulates another psi of phase, so we now have e to the minus j 4 psi. That can transmit, or it can reflect. It transmits by tacking on a T21, and it reflects by tacking on another R21. So we have an R21 squared here. Well, that wave, that reflected wave, transmits another psi of phase we accumulate. So we're up to e to the minus j 5 psi, and that can reflect or transmit. For the transmitted wave, we tack on a T23. For the reflected wave, we tack on another R23. That travels backwards, accumulates yet another psi of phase. So now we're at e to the minus j 6 psi. That can transmit or reflect, and this continues forever. There's an infinite number of waves that reflect, that transmit, and that bounce back and forth within this slab. It's actually quite complicated. If we wanted to calculate the overall reflection, we would have to add all of these infinite number of reflected waves. And remember, these continue going downward. Likewise, if we wanted to calculate total transmission, we would have to add all of these up, and we have an infinite number of terms of these because they continue going downward as well. Now on to the math. Let's calculate a nice, convenient, but general expression for the overall reflection coefficient R. So this will not be the reflection coefficient of a single interface. This will be the overall reflection coefficient from this slab. Well, just looking at all the terms in what we just analyzed, we can just write these discretely. Staring at this long enough, I'll recognize that, not including the R12 term, but everything else, which is an infinite series of terms, can be written as a summation. And maybe it'll take you a few minutes to realize we can write it this way. From there, I'll notice some common terms that really don't have an n power associated with them. We can bring those to the outside of the summation. So we're factoring out this term on the left, and we're left with some term on the right that only had these n powers in it. So we can factor out the n power here and just do this on the outside of parentheses. And there's a reason that we did this. So at this point, we'll take this single expression for this infinite number of terms and plug that back into our overall reflection. And on the next slide, we'll figure out why on earth we put it in this form. There is what's called a geometric series, and some factor a times x to the n power. If the absolute value of this x is less than 1, in other words, these terms will continue getting smaller and smaller and smaller at a sufficient rate, this summation has a closed form expression, and we can write the answer this way. And it turns out the summation that we wrote for the overall reflection coefficient is a geometric series, and we can write it as a single closed form expression. Let's go ahead and do that. So this is the expression that we had on the previous slide. Now looking at this summation and comparing it to the summation up here, we recognize what x is. And we'll look at the absolute value of this stuff, and that is absolutely less than 1. So that means this is a geometric series and it will converge. So instead of writing the summation, well, I can now use this expression, this closed form expression for a geometric series, and just write that immediately. And then the last thing I'll do is just bring this collection of terms into the numerator here to write it a little bit more compactly. We're almost done with this. We have a lot of terms in our equation, and we can simplify things. Going back to the beginning, remember we had a bunch of different parameter relations, and we can use this, and it turns out we can put this big ugly expression for R that we derived on the previous slide just in terms of R12, R23, and psi, just using these above four relations. So anywhere I see one of these terms above that I can replace, I do all those replacings, and here they are. So I've replaced three things here. So I can chug through the math, I can simplify a bit, and I end up with a final expression for R with a reduced number of terms. And if you Google this, reflection from a dielectric slab, this is the equation that will come up, and now you've seen how it's been derived. Similarly, we can calculate the overall transmission coefficient, and this will also become a geometric series. So just looking at the expressions that we derived in that original analysis of the waves bouncing back and forth, we can write the overall transmission coefficient as this infinite series of terms. Well, staring at this long enough, we can put that into a summation. Our job now is to factor out all of the terms that are not raised to an n power and bring those to the outside of the summation. So it turns out we'll factor out a T23, T12, and an e to the minus j psi. And what we're left with are a bunch of terms raised to the n power. So I can put those terms in parentheses and then put the n power on the outside. Well, that's a geometric series, and so it has a closed form answer. Like the reflection coefficient, we would like to reduce the total number of terms. So we go back to these same relations and we apply that to our transmission expression, and we do all the substitutions, and we can simplify the algebra a little bit. This does not clean up as nicely, I think, as the reflection, but we do get a decent expression for the overall transmission. And this is a general expression, just like the reflection coefficient. It'll turn out the overall reflection and overall transmission coefficient are related. So these were the two expressions that we derived for the overall reflection and transmission coefficient. Observe they have the same denominator. That's what's going to let us relate these. So they have the same denominator. So what we can do is solve both of these equations for the denominator. So I'll just really replace R and its denominator and T and its denominator. So that's this step. We solve for that denominator. Well, since this expression equals that denominator and the expression over here equals that denominator, it makes sense we would set the expression on the right over here equal to the expression on the right over on the left. Those words didn't make a whole lot of sense. But anyway, we'll set these two equal, and we almost have our relation for R and T. I like to bring R and T over to one side and everything else over to the other. And so that will be our final expression for how T and R are related for a slab. And it's important to remember this R and T in this relation are not for a single interface, but for a slab. This scenario of a dielectric slab seems to come up mostly in two different configurations. The first one, called the low finesse configuration, has very small reflections. And what we can see happens when the reflections are small, we get a response that's very cosine or sine-like. And you'll find these a lot in things like fiber optic sensors or gravity sensors that are using optical interferometry. And very often they'll use reflection air to glass, so there's about a 4% reflection. And there's essentially a pretty good cosine response from that. In the second one, it's when there's very strong reflections. And you'll find this a lot with things like lasers that have to have a high reflectivity to get a strong enough resonance to produce a population inversion. And there you'll see more of a comb action where it's a series of impulses instead of a series of sines or cosines. And of course, if it has moderate reflections, it'll be somewhere in between. But in application, it really tends to fall into one or the other. Let's look at the math of this. So we'll start with the general equations for overall reflection and overall transmission. And we'll play with the math a little bit. The first thing we want to do is to simplify this just as a way of thinking. And let's let this be a symmetric slab, in which case the R23 would simply be just the negative R12. And in effect, we're putting everything in terms of a single Fresnel reflection coefficient for that first interface, for both transmission and reflection. We can simplify that a little bit, and we end up with these somewhat reduced expressions. Now let's look at what's in the denominator. We have a 1 minus something. Well, this complex exponential, we can kind of think of that as just being on the order of 1. But this reflection coefficient is squared, is multiplying that. This is already pretty small. We can think of this as being like 0.01 or 0.05, somewhere around there. So when we square it, it becomes a 0.00 and maybe even a third zero there. So it becomes very small relative to that 1. And in a sense, we can set the denominator equal to 1 for both of these expressions. So in the end, we end up with somewhat general equations for the overall reflection and transmission from a low finesse cavity or a low finesse dielectric slab where there's small reflections. Let's keep working with this math because we know that it has this cosine or sine response. Let's let the math tell us that. So we start with this expression from the previous slide. Well, I want to get a sine or a cosine out of this, and I'm looking at this term. And I know there's a definition of sines and cosines in terms of the complex exponentials, but I really need the difference or the sum of two complex exponentials to do that. Well, I can actually do that if I factor out an e to the minus j psi from what was in this term. So the term on the right ends up just being an e to the minus j psi, because when multiplied by this one, I'll get the minus j2 psi. But this one over here is an e to the positive j psi. Now, recognizing the trig identity, this combination of exponentials ends up being j2 times sine of psi. And there's the introduction of the sine. I'll just rearrange terms a little bit because the next thing I want to do is look at the absolute value. Because those plots we had, we were looking at reflectance, that was the absolute value squared of that. So we want to look at the absolute value, and we have the product of a bunch of terms here. So really it's the absolute value of each of those. Let's think about them one at a time. Well, the magnitude of j is just 1. The magnitude of 2 is just 2. The magnitude of R12, we can't do anything with that. We just have to keep writing it as magnitude R12. The magnitude of that complex exponential, that's 1. And the magnitude of sine phi is just written as sine phi. So now we can get rid of those absolute value signs and write the final equation for the reflection from a low finesse cavity. And as we were expecting, there is our sine phi. And if we were looking at actually reflectance, which is the absolute value squared, we would have a sine squared phi here. What about the case of oblique incidence? So in this case, medium 1's on the top. We have a beam coming top down. I did it that way because we could fit in a lot more reflections than looking at it horizontally. So we have a beam coming in, and rather than give it an amplitude of E0 like we did before, I'm just giving it an amplitude of 1, and that just helps all the terms after that be a little bit shorter because we don't have to put the E0 in there. So the wave on the other side of the interface is just simply T12. The reflected is R12. And there's an angle theta 2. This has the effect when the wave propagates through medium 2, it changes how much phase gets accumulated. And in fact, here is the revised equation on the right for that revised phase. It's still K0 N2D, but there's a cosine theta 2 in here. So as that angle increases, it's accumulating less and less phase. But it's the same configuration. The beam bounces an infinite number of times. Each one of those bounces produces a reflected wave and a transmitted wave. We sum all of them, it forms a geometric series, and we get the same expressions actually for overall reflection and transmission. And that's because the only thing that has really changed is the expression for psi, which is super useful. That means we can generalize this in several ways. So if we have normal incidence and no loss, this was the absolute first thing that we analyzed. This psi is just K naught N2D. Oblique incidence and no loss, we just looked at that, and we end up adding a cosine term. And this theta 2 is the angle, not the angle of incidence, it's the angle in that second medium after it's been refracted. Now, if we have loss and normal incidence, there's no cosine, but we still have a K naught N2D. It's just that N2 now is a complex number. It has a real and an imaginary part, the real part being the ordinary refractive index describing phase accumulation, and the imaginary part being kappa, that's called the extinction coefficient characterizing loss. And then everything, oblique incidence and loss, well, K naught N2D, cosine theta 2, and this N2 is a complex number because it's lossy. Another configuration comes up a lot, and if the slab is symmetric, and very often when we measure something like that, we measure transmitted as something called S21 and reflected as S11. There's a larger theory behind these S and the indices called network theory. I won't get into that here, but suffice to say that measuring the transmitted wave as S21 is so common that many engineers, they'll just say S21 and like everybody's supposed to know what they mean, or S11 for reflection. It becomes a very common thing to say. Well, if we have a symmetric slab, meaning whatever material's on the outside on the left is on the outside on the right. Well, here we will just have a single reflection coefficient, not to be confused with the overall reflection coefficient. We're running out of letters here. So this is the reflection coefficient for a single interface. And really it's the reflection coefficient of the first interface, and the second interface will have a negative sign because on the first interface we had a wave going, say, from air into a dielectric. The second one we have going dielectric into air, so there's a 180-degree phase shift. But we could just write it as either R or negative R. Again, not to be confused with that overall reflection coefficient we were talking about. Then the transmission coefficient, the phase accumulation, it's a single pass e to the minus j psi, and then our psi is K naught N2D. Given that, we can calculate our scattering parameters from the single Fresnel reflection coefficient and the single Fresnel transmission coefficient. So if this comes up enough, I think it warrants having these equations. So let's do an example. Does Wi-Fi get through a glass window? Well, let's find out. So your typical window is made of fused silica. That has a refractive index around 1.52, and I'm saying the window's about 3 millimeters thick. They vary, but that's an average thickness that I could find online. So let's go through the solution. Well, first, what is the transmission, the equation for transmission through this slab, the overall transmission? And we had derived this equation earlier. Well, from there, we need values for R23 and R12 and even the psi. So the R12 is the impedance of the second medium minus the impedance of the first divided by their sum. We can put this in terms of refractive index. For optics problems, when you're given a refractive index, you can assume that the relative permeability is just 1, and you can convey that completely through the relative permittivity, and we can reduce a problem that has impedance in it to refractive index. Notice the terms have swapped. This was A to 2 minus A to 1, but now we have an N1 minus an N2. So those little indices have swapped, and that's simply because the impedance is actually 1 over epsilon, and so the indices end up inverting like that or switching places when you simplify the math. So I can plug in the numbers and I get a reflection coefficient at the first interface of minus 0.2063. At the second interface going from dielectric to air, let's say, it's 1.52 minus 1 over 1.52 plus 1. We get now a positive 0.2063. We knew that this would be the same number with opposite sign. And then we can also calculate psi, and that ends up being 0.2292. Let's continue with the solution. We just got all these numbers. We'll plug it into our equation for the overall transmission, and we get a complex number over here. So what on earth does that mean? Well, it's complex because the transmitted wave can change its amplitude and its phase. So it makes sense we have a complex number. The transmitted power is really going to be the absolute value squared of that transmission coefficient, and we get 99.52% transmitted through the window. So the conclusion here is that windows do absolutely nothing to block Wi-Fi. Just not enough of an electromagnetic response from the fused silica glass to do anything. Another great example of the dielectric slab is oil on water, right? There's no rainbows in oil, there's no rainbows in water, yet when you put oil in water, suddenly there's rainbows. And it's an interference effect. So imagine you got a beam of light coming in, right? Some reflects, some transmits. It's bouncing back and forth in this oil film. And these all add together and they interfere with each other. And the interference is important because when you change the angle, you change the way in which they interfere. So when you're looking at the rainbows on water, oil and water, you're really looking at this at different angles. And that's why you see the different colors. If you move your head, you would see these colors move around. Last, I want to show you a time domain simulation of scattering from a slab. Everything we just did was the steady state analysis. Let's look at the transient response. We have a wave coming in. Some of that starts to reflect off the first interface. Some is transmitting, but it hasn't reflected yet. Now it's just beginning to reflect off the second interface. It's starting to come back, and that wave, that second reflection there, now it's hitting this first interface, starting to come through, so we can see the red, the reflected wave starting to fluctuate, and that bounces back and forth. And my point here is this is going to have to run for a while before it resembles what we would calculate using all the equations we just stated. So even though you designed this anti-reflection layer and you want to hide something, for example, well, if somebody has a transient radar or some kind of transient system, they're still going to be able to detect that that is there because there is this reflection at first when that wave first hits the device, simply because those resonances haven't established themselves. The resonances that would produce the reflected wave, that would produce the interference to zero out reflection. So that's really important to realize. Very often you can defeat these things with something that looks at the transient response. And I think that's really interesting. From the bottom of my heart, thank you so much for using eImpossible. I want to create more videos and I want to continue to improve how electromagnetics and computation is taught online. To do that, it will really help me if you can like this video and subscribe to our channel. I also want you to know we have a lot more content that you may not be aware of. See everything we have to offer at eimpossible.net.